Hi everyone, welcome to this lecture series. We're starting our new unit, which is all on Newton's laws. So I'm going to give you an introduction to Newton's laws here, and usually I spend way more time on talking about it, but as you kind of realized already, this course is much more accelerated. But I will talk about Newton's three laws and talk about mostly about why things move. That's exactly what they describe. And then what we're going to do is we're going to take Newton's second law and really push it forward in the next couple of lessons. And then we're going to push forward Newton's third law in our concepts of momentum when we do that later as well. Newton's first law we use we use it all the time, but it's not something we focus on only because I don't even know how to describe it. I don't know how to describe it. I'm going to leave it as right now, and then I'll talk more about it as we get into it. So, like I said, what I'm going to do is talk about Newton's laws. And even though you probably have heard of these before, I like to translate them into something that sounds more like applicable when it comes to doing physics and applying it to everyday life and whatnot. And then we're going to talk a lot about what forces are. So I'm going to go through these kind of quickly, like what a force is and how we model them and how we draw this thing called a free body diagram. And then we'll kind of finish off with the difference between mass and weight because we actually use Newton's second law to describe weight. And we'll talk about weight in other planets because, that's cool stuff right there. And then the next video is when we launch into, like I said, Newton's second law, which is deceivingly simple. It's F equals ma, but we'll find out very quickly that it's not as trivial as it seems because it is a vector problem. And when it comes to adding pushes and pulls, we can't just take two numbers and add them together if they're going something like this, right? You can't just add these things and know that 10 is which way, up or this way. It's actually a combination of the both, but it's not 10 if these were both 5. I didn't mention that, sorry. I was thinking that. But anyway, so this is really a foundation lesson and as we progress further in the course. So why do things move, right? So this is exactly what we're talking about. So we actually didn't address that issue in the first lesson. We talked about motion, how to model it, not why it's moving. Notice I never talked about that. And I kind of alluded to Newton's first law when we talked about projectiles as once the object leaves your hand, it keeps its motion. Now, obviously, I have to apply a force for this to happen, but theoretically, if gravity wasn't here and I pushed it up, this would keep moving up at a constant rate until another force encountered it. This is all about Newton's laws and how to apply them like that. My phone on silent, that'd be helpful. So Newton's laws really talk about why things move, and not only how single objects move, but how systems move. So I have this big, solar system here. If you recognize it, it's our solar system. But anyway, Newton's laws do describe why our solar system behaves the way it does. So it's not just for one object, but it's for a system of objects. In fact, next lesson I'll talk about these things called systems. And it's a really big word for things that are connected to each other in some way, shape, or form. Whether it is a physical, something that actually physically comes in contact, or you have a rope that's pulling two things. So that's a system interaction. So we'll talk about all of these as we go through. So here they are. These are Newton's laws of motion. So objects in motion stay in motion. Objects at rest stay at rest unless acted upon by outside force. I bet if I had quizzed you or asked you, you probably would have known what that was, right? So I'm going to, of course, talk more about what that means. Because like I said, I think most of you can probably say this in your sleep, but maybe not know how this applies. So I'm really going to talk about how each one of these apply in everyday situations. The next one is not well known because it really is the equation F equals ma. But let me just describe what it says in the physics sense. Net forces are proportional to the mass and acceleration of the object. So in other words, we can define a force if an object has an acceleration. That's kind of what this says right here. So if this thing is changing its motion, it has a certain amount of mass, there must be a force present, and this is how much it has. And we'll talk about that. And we'll spend a lot of time in that law. And the last one, this is probably one of my favorite because this is probably the most mind-blowing one, I think, actually. Is for every action, there's an equal opposite reaction. Once again, I think all of you have heard that before, but I don't think a lot of you actually know what it means and what it implies. Because when I tell you, it blows your mind. Like, it totally does. You're like, what? What are you talking about? Crazy, right? So this is how I translate them and what they actually mean to me and how I apply them in everyday life. So I have my little trademark, the Granucci translation of what these mean. So first of all, the first law, objects in motion stay in motion. What it really means is that all objects will maintain constant velocity. No force is needed for constant motion. Like what? So actually, I'm going to expand on this and on a sheet of paper just to, I think I actually expand on all of them. Yeah. All right, fine. No, okay, I should change my mind. Okay, of course this thing is, okay, so what this means is that, okay, now my thing is just going crazy. Okay, finally. Connected. Newton's first law. So essentially what this means is that a couple things that hopefully come to mind. Number one, objects keep their motion. So once it's moving, it stays moving. You know this from riding a bicycle. You know this because it's really laggy. It's amazing how laggy this is. From riding a bicycle, because we know from riding a bicycle that if you take your, if you stop pedaling, it basically means, I can't believe how laggy, I always say this. So when you stop pedaling, the bike keeps moving. And you know that if Newton's first law was not true, if you stop pedaling, your bike would come to a full stop. And we know that's not true because we've done it before. Or rollerblades, or your car. We can take our foot off the gas pedal and the car keeps moving. Now, there's an outside force that affects us, which is friction. But we can take our foot off the pedal and the car keeps going. So those are some really important features of this. I always like to talk about Newton's first law when it comes to starting and stopping too, because when you're sitting in your car, for example, your body keeps your motion, and rest is a type of motion too. So when you're sitting in your car and you are about to start your car, right? Your body, and you press the gas, your body goes backward, right? Especially if you do it really fast. But what's happening is you keep your motion. Objects in motion stay in motion. So what's happening is you are actually still at rest and the car starts to move. So it's not that you are going backwards, but the car is hitting you from behind because you are at rest. So the car is doing this. So we feel going backward, but in reality, the car is meeting your back and pushing you forward. So I always call that the lurch forward. So the car example. Actually, this is the lurching back from rest to moving, right? You have what is called inertia. Now, inertia is based on an object's mass, and it's the ability to keep its motion. So naturally, the bigger the mass, the more inertia. So for instance, in the car example, the car has way more inertia than me because I am less massive. Now the car example can go the other way. You can go from moving to not moving, right? So if you're in the car again, and you're moving, and you step on the brake, what happens? You go forward, right? Well, that's because you're moving and the car has stopped. So, in that car example, now what happens is your body has inertia. It keeps moving. While the car stops. So if you think about what's happening there, is that your body, the car stops, so the belt comes to you because you are moving, right? And you know that because we have seatbelts. Seatbelts are exactly what's keeping us there, because always we would keep our motion. So that's Newton's first law. We always keep our motion, and the way we keep our motion is dependent on inertia. The more inertia we have, the more likely we'll keep our motion. So, for example, when it comes down to the size of a car, right? So a car versus a truck has way more inertia, which means once it's moving, it stays moving, and it's hard to stop that truck from moving. You know that without physics. You know, if you were not, you wouldn't do this, but if you were to go up to a car and just try to a truck and try to stop its motion, it's really hard to do. It has lots of inertia, which is also why if you are ever stuck behind a car that's very large, like a truck or anything, it's going to take them a long time to start moving and stop moving. So if you're in a rush, don't be behind that truck. So these are just some quick examples. And the last example is, of course, that tablecloth example. Unfortunately, I just really don't have a great place to do this. But the tablecloth example is if you take, I do this live in class. So again, another unfortunate thing about teaching online is you have the tablecloth, right? And you have a plate or some object on here, and you rip the tablecloth off. And then the table's left. And then the plate's there magically, right? Well, it's not magic. It's actually having to do with inertia. An object at rest stays at rest, so it doesn't matter if the tablecloth moves or not, right? So let me show you a quick couple demonstrations with that. These will be live. Let's see. I usually do the Inertia Club, which are a bunch of, these are for some of my former students, doing the tablecloth demonstrations. So here we go. This is something we do in class too, or could have done in class. Taking the water and doing this tablecloth demonstration. See, anybody can do it. Penny and a tape is a pretty fun one where you can see that it goes on. Yep. Pennies and the knife or the spatula, that's a good one too. The egg and the beaker is another one I like to do live in class too. Here's my students doing it. Doing a pretty good job. And there's bloopers, which is fun, but we're going to ignore that for now. But anyway. So another thing, since I have this open, is this. So this idea actually came from Galileo, surprisingly, even though it's Newton's laws, right? Now, Galileo was pretty smart because, first of all, he figured out that all objects accelerate at the same rate regardless of their size. So that's pretty smart from him. Another pretty smart thing he thought about was his thought experiment. He thought that, actually, before I show you this, I'll show you this. So if you take your smooth snow, right, he was thinking of what if there's no friction? Now, we take this for granted because we understand there's friction, but back then, they didn't know about friction. They thought the state of all objects was to come at rest. That was originally what was thought. So, but Galileo it just didn't sit right with him. So he thought about this. He's like, what if I had some snow and I had a person on the sled? This is actually not what he thought at all, by the way. He did a ramp experiment, but that's okay. So if you imagine this, you take your sled and you go on the sled and you go on the snow. You go for a while and then eventually you stop. Well, if we change that to ice, right? We know that ice has less friction, and then you would go way farther, like that. But what if you had ice that didn't have friction? What would that object do? It would go forever, right? And that was the first time he was considering the concept of, number one, friction. He's like, oh, there must be something slowing this object down, because without it, the object would never stop. That's crazy. So if you were to apply a very, very small and simple force, oops, sorry. There we go, I'm going to apply a very small force. And there it is. A very small force. And there it goes. There's no friction in this simulation. So it's going to be incredibly boring, and it's just going to keep going pretty much forever, just like that. So as long as there's nothing slowing it down, why should it stop? And that's exactly what Galileo thought about. Now, unfortunately, we are constantly around things with forces. So first of all, gravity is one of those things. And then secondly is friction. So right now, I am pretty grounded right now with gravity. But technically, if I, how should I say this? I'll say it like this, yeah. So technically I'm grounded right now by gravity, so I'm at rest and I stay at rest. And I could move a little bit, just like that with my wheelie chair, but same thing. I actually have an enormous amount of friction that slows me down. So we don't see this effect. And usually the only time we really see this effect is like very low friction areas like ice. Or the other time is we use our thought experiments that go into space, because in space there's generally less forces around. Now there is forces around, but there is less that kind of contribute to that. So as you can see, this is pretty boring. Notice there's no force here. I applied a force before, and I can do that to change the object's motion, but I can put it back to 0. And it still is moving. That's the important thing, that it keeps its motion. Objects in motion stay in motion. And no force is needed for constant motion. No force is needed for constant motion. Everyone's going to get this question wrong. I know it, because it doesn't sit well. So if I throw a football in the air, it stays in the air and moves because you don't need a force to keep it there. If I want something to move to the right, I do need to apply that force, but once I apply that force, I don't need to keep that force there. That's what it means. So number 2 basically says that net forces cause accelerations, or in other words, a change in object's motion. Acceleration depends on mass and force. So even though it's F equals ma, I like to think it as a is equal to F divided by m, and I'll show you that a little later too as I talk about it, because I think it just makes a little more sense in terms of understanding what it actually means. It means that so all things keep constant motion, and when things are accelerating, then there's a force present. And you need a force present to make something accelerate. So it's kind of a back and forth with that, and it's based on an object's mass. And lastly, the most shocking, I think, of the 3 laws is Newton's third law. All forces come in pair. First of all, action-reaction doesn't mean anything, at least to me. What it means is that all forces have a pair. Force, force, pairs. And these pairs always are the same strength, but facing opposite. So action, reaction, same size, no matter what. This is weird. If I push on the table pushes back on me in the exact same amount of force. If I had a force sensor, I would show you that this is in fact true. In fact, no matter what I did, whether I lightly tap my hands or I give a clap, if I lightly tap this one and not move it, if I slap this one and not move it, it doesn't matter. The forces are the same between those 2 objects, which doesn't make any sense. I know, it's weird, but it is true. That was that thing, and I just did that. So yes, I got carried away, I guess. Went off my slides. That's okay. So yes, so back to Newton's first law. Friction slows things down, and that was Galileo's realization. And then, of course, from Galileo's work, Newton took that work and made it into the laws of motion. So it was heavily influenced by Galileo's work. But the natural state of objects is not coming to rest, which was originally believed. It's the actual natural state of objects is constant velocity. And rest is a form of motion. It's a very special form of motion, but that's also included in our law, so it's very powerful. And yes, we talked about this. Objects will maintain constant velocity. I'd like to say that objects keep their motion. If you're at rest, you keep staying at rest. If you're in motion, you keep staying in motion. The only thing that changes those things are forces. Okay, moving on. So, Newton's second law. So like I said, this is Newton's second law in the physics kind of perspective. But basically it says that if something is changing its motion, and of course we have the mass, we can quantify it as being a force. So something that's moving, that's very small has a small force applied, and if something is big, it needs a big force. I think you know that. I love my shopping cart example. So let me do my shopping cart example as we do this. Actually, let me see where I'm going with this. Yeah. So the larger the mass, the less the acceleration, the larger the force, the more acceleration. So I'll put this here and do my shopping cart example. So this is Newton's second law, and this is how we'll actually apply it and use it. So we're definitely going to do F net equals ma net. Now net means if there's more than one force, we're going to squish them into one. That's next lesson. So right now we're not going to go into we'll go in a little detail with that, but not too much detail. But I'll show you what that means. I like to think conceptually in this form. An object will change its motion, acceleration, based on how much you push it and how much mass you have, right? So like I said, I like to do my shopping cart demo, and it's, man, so hard to teach online. Oops. So let's look at N2. Shopping cart example. So imagine you have your shopping cart, right? I'm sure you've all done this at some point. And you're shopping. Yeah, this is a great shopping cart. Person. Put some hair on that person. It could be me. Why not? Excited, shopping. Every once in a while I get out. I think I should probably put a mask on that person, but we'll just go with it. This is COVID-free time. Okay, so when you have an empty shopping cart, right, you have a little mass. And it doesn't take that much force to push it, right? So we can change the object's motion. We can have an acceleration. But over time, you go shopping, right? So let's see if I can draw this person again. Oops. And you have your two arms for the shopping cart, the wheels, oh boy. Shopping cart changed while you went shopping too. And you buy your food, right? I don't know, toilet paper, right, and your sanitizer and your apples, because why not you need some apples and oranges and I don't know, a full shopping cart, right? Well, what's different? The mass, right? It's going to take way more force to push this at the same acceleration as what you had before, right? You know this through experience. It's easier to push less massive objects. You don't need physics for this. You know this already. But in case you needed physics for this, that's what this is about. Notice that, I'll write it down here, is that the m is on the bottom here, right? When m is smaller, a is larger, which means it moves more. Changes motion more, right? That's what A means, changes motion more. It's easier to move it. This is the empty shopping cart. But if you have something like this, with a big mass here, you're going to need a lot more force. Because as the m is larger, then A is smaller. It's not going to move as much, right? Because you have more mass. It doesn't change its motion, so there's less change in motion. And just for the effect of everything, let me change it so they actually look like big and small. So I'm going to make these different. So we're assuming the same force. We're not going to push it any different, but this is a teeny tiny mass with V and big A, and this is this with a teeny tiny A, like that. So, and you know this too. Have you ever done it where, I know as a kid when I load up that shopping cart and I used to help my mom, I used to like jump on the shopping cart and you'd ride it like, wee, you know. But then all of a sudden you put all the groceries in it and you're riding that shopping cart and you're coming to your car and you're like, well, I can't stop it because it's so massive. It's hard to change its motion. This is all Newton's second law. So you kind of know this already. You don't actually need physics equations to tell you these things, but the more you push something, the more you change an object's motion. You knew that too. Even with the shopping cart, if you push twice as hard, the object will move twice as much. Of course, the mass does affect how much it moves. So if it's heavier, then it's going to not move as much as if it is lighter, but either way, it's still the same. And the more massive is, the smaller the change of motion. If a bug hits your car, it's not going to set the car backward, right? It doesn't do that. It's not a big change of motion. Does it change the motion? Yeah. Do we see it? No, it's too small. But this is how we'll use it. So, like I said, the force net means if there's multiple forces on it, if we squish all those forces down into one, that's the value of the net force. I will show you an example of what I mean by this. M stands for mass, always measured in kilograms, so keep an eye out for problems because, of course, they're going to change things up on you into grams. Make sure we're in kilograms. And A is for acceleration. Now, the word net is here because the net acceleration and the net force are in the same direction always. In fact, I'll just go ahead and just put a red mark here. So that's what this is kind of referring to. So the net force and the net acceleration are in the same direction always. So let's use our physics to put common sense to this. So in other words, if I push this forward, the object's going to accelerate forward. That's what it means. If I have four forces and my biggest force is forward, then I'm going to accelerate forward. And that's exactly what the net force means and net acceleration. So you're never going to have a case where if your net force is down, your object moves up. That's not true. That's never going to happen. Well, let me be careful with that. I'm going to be careful with what I just said. What you're not going to have is if an object is being pushed down, that the net acceleration is up. That's not going to happen. Now, the motion can be up, so that's why I want to be careful. So I'm going to repeat myself. You'll never have a case where you have a net force down and a net acceleration up. They're never going to be the opposite. They'll always be together. So just careful with that one. Newton's third law. Newton's third law says for every action there's an equal and opposite reaction. But essentially, what it means is that all objects experience the same force, regardless of their mass. So, fun fact, the Earth pulls on the sun as much as the sun pulls on the Earth. They're the same value. What? How is that true, right? But you're like, oh, but the sun is clearly pulling the Earth around, the Earth is not pulling the sun around. You're right, because that does matter. But when we talk about systems, two objects, they'll feel the same force. If we're talking about one object, then that object will accelerate. So that's the difference. We're looking at two objects, but it is true. I am actually pulling on the sun as much as the sun is pulling back on me. Or let's use the Earth because that's a better example. But I have less mass, so I'm not going to see any effects. Or the Earth's not going to see effects from me, but I'm going to feel the effects from Earth because I have less mass. So that's kind of how it goes. But that's true. All forces have the same value, just opposite in direction. And these are what we call action-reaction pairs. So if the tires push on the road, then the road will push back on the tires. In fact, that's how driving works. If the road can't push you back, then you don't go anywhere. Ice, sand, right? Think about those cases. Leaves. The road can't push you back, then you don't go anywhere. Your tires just spin. Same thing with rockets. Rockets push on the gas, and the gas push on rockets. So back in the 50s, right before we started, launching rockets into space, people were like, well, how do you propel in space? There's no air to push on. Right. We don't push on air. We push on the rocket. Just like you take a balloon and you blow it up really big and you let it go and it goes everywhere. That's exactly how rocketry works. Imagine. The air inside the balloon pushes inside the wall, pushing the balloon this way, and the air leaves that way. Pretty cool stuff. Man pulls on spring, spring pulls on man, earth pulls on ball, ball pulls on earth. Notice the formula. Two object, same force, opposite direction. Look at the arrows in all the cases. These are action-reaction pairs. You will have this as a multiple choice question, but you must be very, very careful on how I ask this question. So imagine a bus and a bug collide. Which one feels the greater force? Is it the bug, the bus, or is it the same? Which one feels the larger acceleration? The bug, the bus, or is it the same? So I'm going to quiz you on this right now. Okay. The answer is the same. The bus and the bug feel the same force. Mind-boggling. I know. You're like, how can that tiny little bug push back? Well, it can't. But it has to, because it has to follow the laws of physics, which means that bug will die because it can't push, because it accelerated too much that it literally splats on the windshield. That's how we explain that death with the bug. So yes, the bug feels more acceleration because it's less massive, but they both still feels the same force. Now, the force that the bug and the bus apply is small. It doesn't actually push the bus back, but the bug will definitely feel it. So, kind of like I was describing before, it's all about the mass. So when two objects interact, they always experience the same force, but different accelerations based on their mass, not math. I'll say it again. When two objects interact, they experience the same force, but different accelerations based on their mass. So this is how we apply, and notice we're applying Newton's second law when we do this as well. So let's talk a little business here about forces. So what is a force? I'm not going to read this. This is for you to read later, but it's a push or a pull. So that's when we talk about forces. Just imagine thinking being pushed or pulled. Forces act on objects. So we're always going to look at the perspective of what acts on an object, not by an object. Notice that. What forces act on the object, not by the object. So you'll get used to this terminology as we go further along. Force is a vector. In other words, it has a value and a direction. So when we push something, it's different than when we pull something, right? We have to model that. And of course, we use arrows to model that. So if you're pushing, it's going to go toward, and if it's pulling, it goes away, depending on our perspective. And we use arrows to model that. In fact, your lab is going to be, how do you add these things? How do you add pushes and pulls? And how do you add vectors? You need vector, technically we're doing vector calculus, but I won't tell you that you're actually doing third semester calculus. It's okay, you could do it, it's fine. But the whole point is that you can't just take two numbers and add them up. It doesn't work that way when we're working with vectors. So the units for force are typically newtons. That's a metric unit, but you're probably more familiar with them as pounds. If you weigh yourself, you're weighing, that's a force, it's a weight, and we measure it in pounds. But in physics, it will be in newtons. Excuse me. So like I said, when we do net forces, we're going to take all those forces and squish it into one, is the way I like to describe it. But the physics way is to say all the sum of the forces acting on the object is the net force. So it's displayed either as a summation or as net, because they both mean taking those forces and adding them together. So it actually means that we can have an up force and down force. We could have forces that cancel. Now, what that means is that the object doesn't feel a net force. It doesn't mean that the objects do not experience forces, right? So here's my water. I put this on the table. Now, the table pushes back up on this object. If not, it would go through the table, right? I mean, it needs to be pushed up on something because what's causing it to go down is gravity, right? If I let this go, we can see that's true. So what's happening? Gravity's pulling this object down, and the table's pushing up. Now the table's pushing up with exactly the same amount of force. I know that because it's not rising, because if these were uneven, this would go up. And it's not bigger downward because the table didn't break, right? You can have a case where the forces don't balance. They could break the table. But these are a case when the forces are balanced. So the net force on this system is 0. The sum of the forces, the down and the up, cancel. But there are 2 forces acting on this object. It doesn't mean that there are 0 forces acting on the object. So there's a distinction there. So here's a quick 1D idea of net forces, just to get you in the idea of thinking about this. And as we move forward, of course, these will get much more complicated. But what we say and what a net force is, for example, if I have 2 ropes and I'm pulling 5 newtons to the right on each of those ropes, it's the same model. I can model it the same way as one rope pulling it with 10. That's net force in a nutshell. If I pull 5 to the right and 5 to the left, it's like I'm not pulling it at all. That's the net force. If I have 10 to the right, 5 to the left, how many do I have as the net force? Select your answer. That's right, 5 to the right. What if I have up and down and right and left? So notice that you could have multiple forces, but we still can do a net force. Ups cancel, the down, the 5 and the 5 cancel, and the 52 and the 22 all combine to a one single force going to the right. So basically, this force diagram is identical to this force diagram. That's what a net force means. And guess what? It's way easier to work with one force than there is to work with 5. In fact, not only that, but you can only work one net direction at a time with F equals ma. Always, you can't use the equations. So there's 2 types of forces. There can be contact forces or long-range forces. Now, most forces are contact forces, things that actually physically touch, like friction is a contact force. This force that the table's pushing up is called a normal force because it pushes perpendicular, and perpendicular is 90 degrees, which is also the name for normal. All surfaces. So the normal force is a weird one because notice that this is pushing straight up, right? As soon as I angle this, notice that it's pushing at an angle. So the normal force, if this is a wall, right, pushing out. And if this is a ceiling, it pushes down. So this is the normal force that I'm modeling here. It's the push from a surface. Good. Making sure this is in fact black, which it is. Good. Oops, I'm touching things I'm not supposed to. Here we go. And then there's long-range forces. The only one that we will work with in this course is gravitation. So in other words, I don't have to touch the earth to see that this is working, right? That's what a long-range force means. The other 2 is electrostatic force, so using static electricity, and the other one's using magnetism. But we're not going to use magnetism or electric force in this course, so you can kind of put that out of your mind until you do Physics 111. Drawing forces, we're going to use vectors, so we're going to use arrows. The size of the arrow tells us how big that force is. So if you draw a teeny tiny arrow, that's a small force. This is a big force. And the direction. We have the tail and the head of the vector. Now this points in the direction that we're going in. I hope that seems pretty obvious. I do talk about the head to tail method of adding vectors. So just to be very clear, this is the tail and that's the head of the vector. We're going to draw free body diagrams. What free body diagrams are is taking one object and modeling all the forces that act on this object. So, for example, if we have a bucket of water being held by a string, what we're going to do is replace that bucket instead of with a physical drawing with a nice box because it's just easy to draw. And we're going to model the forces that are acting on it. So we have to analyze situations. In the next series of slides, I'll give you a catalog. But for now, gravity is acting downward. And then we have the string being pulled up, and that's going to create a tension. Now, they gave us the values. Now, we may be given those values, we may not. But more importantly, we're drawing the forces that act on this. We have a downward force and an upward force in this scenario. So we're going to be drawing free body diagrams. Here's another free body diagram. We're going to do inclined planes, and notice the way the free body diagram changes. Now, people use different symbols for things, so I'm going to keep things, pretty similar to what typical people use, but, instead of, they use F gravity here, notice that, and here they use W for weight. They're the same thing, but notice that it points straight down. Here's that tension again, right? It's going up the incline. We have the normal force pushing away from the surface, and this thing represents friction. So there's some friction, kinetic friction due to motion. We'll talk about that too. And these are all the forces. There are 4 forces acting on this guy. Crazy, right? Even though it looks like only one, right? You can only see this. But the surface pushes, there's friction, and there's gravity. And lastly, I'm going to talk about mass and weight. So I talk about mass and weight because we're going to be calculating weight. When you weigh something in a chemistry or physics room, you're usually taking the mass of the object, if you notice that, right? You're figuring out how much stuff there is. So literally, it's a count of atoms. So when you weigh 1 kilogram, that's how many atoms make up that object. Now, when it comes to, and it remains constant everywhere. So in other words, I'm going to make up an easy number. Say I have 100 kilograms of mass. I will have 100 kilograms of mass because that's what I'm made up of on, whether I'm here or on the moon. 100 kilograms, same. But my weight's different because the weight incorporates the pull from gravity. So if I go on the moon, you all kind of know this already, but you are lighter because the gravitational pull is lighter, which means the acceleration due to gravity is lighter, and you become lighter. So mass is how much stuff you are. Weight is the calculation of how much stuff plus how much pull. Those two together make an object's weight. Now, when we weigh ourselves, we get the weight of us. We get the mass times G, but we usually don't think about it in terms of stuff. So if you want to be that way with your friends, and if you want to lose weight, you really want to lose mass, right? Because you want to lose how much stuff you are. If you want to lose weight, you could just go to the moon, and you could be less, but who's got time for that, and money, and no one's been there, all that fun stuff. But anyway, if you want to be that way, you want to lose mass, not weight, when it comes to losing weight, right? Okay. And yes, technically, planets is one place where your weight changes, but elevation too. Now, 9.81 is typical for sea level, but if you are below sea level, it's actually a little stronger, and if you're above sea level, it's actually a little lighter. It's not much lighter, so Mount Everest, for example, it's like 9.7 instead of 9.8. So, it's not noticeably different, but it is different. That's the cool thing, right? So to calculate an object's weight, you take the object's mass and you multiply it by the acceleration due to gravity of the place you are at. 99% of the time we'll be on Earth, so 9.81. So it's a pretty simple calculation, and it's also what is the downward force. So good news is the force of gravity is always downward, always, no matter what the object's doing. The object's doing a somersault and doing this loop here. The force of gravity always points down. And if this is 1 kilogram, it's not a pen, that would be too heavy. It would be 1 times 9.81. This would have a force of 9.81 newtons. And we measure the force in newtons. Notice that this is in newtons. So just to give you a little background, so notice that on the Earth and on the moon, the mass is still the same. But if we go to the moon, notice the weight is different. The acceleration due to gravity is 1.6 on the moon, and here it's about 10. So it's like almost 80% lighter. So I did a bobcat because, Quinnipiac, right? Bobcats. So there's your bobcat, right? So the bobcat will look the same on both planets. That's the cool thing, too. So they look the same on both planets, but the bobcat will be much less lighter on this planet. Another fun fact, that when the bobcat jumps on Earth, it goes up and down, it's definitely going to have a much easier time jumping up and down on the moon. In fact, it will fall very slow because the acceleration due to gravity is much slower, so you get that moonwalk effect. But the inertia is the same on the moon. So if the bobcat were to do something like this, if it were to zigzag like this, it would actually have the same effect on the Earth and the moon because you're measuring an object's inertia by shaking it back and forth like this. So it has the same inertia. The amount of stuff, its mass is the same. But if it were to jump, it would feel the difference. So astronauts have this issue. What happens is they go on, on Earth, they have these giant backpacks. They're about 100 pounds. I'm not sure if that's the right number, but let's pretend. Or 50 pounds. I think they're 50 pounds. They're huge. So if they were to jump, that backpack, it doesn't matter. But when they walk, it does matter because they actually feel it. It feels heavy because it has inertia. It still has inertia of, I don't know what it is in grams, but let's pretend it's 40 kilograms of the 50 pounds. I don't know what it is. But anyway, the point is they have the same inertia. So anything wiggly will feel the same, but anything jumping will be lighter. Weird, right? So this is just some cool facts. So if you go to other planets, this is how much you would weigh. So if you have a 50 kilogram object, you would weigh 110 pounds in the Earth, but you would weigh 18 pounds in the moon. But if you go to Jupiter, you would weigh 330 pounds. You would look the same. That's the whole point. This is mind-boggling. You would look the same. Crazy, right? So you'd be, someone like me would be like, I don't know, because I'm not, trust me, I'm not 10 pounds. But let's say 400 pounds, right? Like I would look like this. It's mind-boggling. And same thing. You would weigh as much as a car if you went to the sun, but looked like this. So if you're going to terraform another planet, one thing we have to be mindful of and ready for is the gravitational pull, the acceleration due to gravity. If we go to planets that have a bigger gravitational pull, we'll actually have more muscles because we have to counteract that weight. Like every day we move our arms. I know this is not like working out my arms in any way, shape, or form, but that actually goes to building the muscle in our body. So if we go to somewhere like Jupiter, and let's just say we adapt, our muscles are going to be humongous because we have to lift our arms or do whatever we got to do. Or if you go into Mars, it's the opposite problem. The problem is our muscles will deplete because there's not as much gravity. So if you've ever seen the movie WALL-E, right? And spoilers, but WALL-E, they leave the planet because they garbage it so much, right? And the people get they get fatter and fatter. That's because while they're in space, they don't use their muscles as much. And their muscles deplete. So that's a reality. I saw that and I was like, ooh, that's true. It's crazy. You might even heard this too from astronauts having a hard time coming back to Earth because they lose their muscle mass or they have to exercise in space so they don't lose their muscle mass. So lots of really big questions when it comes to exploring and terraforming other planets. So Newton's laws explain why things move. Things move because they're either already in motion or there was a force to set them in motion. So objects keep their motion no matter what. Once they have it, they keep it. So if you throw in a ball, it will keep its motion until something interacts with it. That's when Newton's second law comes in. The interaction depends on how much you push it, its mass, and of course how it changes its motion. But the more you push it, the more it changes its motion. The heavier it is, the harder it is to change its motion. That's Newton's second law. The third law has to do with two objects. And anytime those two objects interact, they're going to feel the same force. But they feel different accelerations based on their mass, so tying it back to Newton's second law. So even though these are three different laws, they actually all work together to explain why things move. Why do we need to know why things move? Well, there's lots of things that move, and we need them to be predictable, like our cars, right? We know that if a piston moves a certain way, that we can calculate literally how much energy or gas you would need to power that car. That's really important. And other things too that move all the time. We need to know how they move and why they move so that they're predictable. So not only like cars, but bicycles, trains. Of course, I can't think of anything at the moment. Motors, anything with motors. So lots of things with motors. And also even stuff like electricity. Just knowing that there's a force there will allow you to understand how things move. So it's very important to make predictions on how things move, and that's why we need Newton's laws. So what we're going to do next is actually really extend F equals ma. We're going to go way beyond what I just talked about. And first of all, we're going to learn how to identify forces in a system and model them using free body diagrams. Then we're going to learn how to use different coordinate systems. So I'll explain what that means when we get there, but basically it just means that we're no longer going to be flat, we're going to be at an angle, and how do we handle that? And then we'll deal with systems, things that move together, and how do we model that motion? Turns out that lots of things move together, they don't move separately. So if you have a gear system, for example, or if you have a pulley system, if you're using heavy machinery, things are going to rely on each other, so we need to make predictable models of how things work. So this is equation building. I'm going to give you a big warning now because the F equals ma will not help pretty much for the rest of this next couple in terms of just applying it on its own. We're going to learn how to write the equation that models the situation. So again, it's all about you telling the equation what to do, not asking the equation what to do. That's what physics is all about. So that will be basically our next couple of slides. So I'll see you in the next set of videos.